looked at some basically the energetics, the energy budgets of climate, and today we are going to look at the correlations between energy inputs and temperatures, basically. So we're going to explore the mechanism by which we have instability in climate, and in the sense of constructing the thermodynamics of this instability. So we will introduce concepts like efficiency in the thermodynamic sense, measure the irreversibility of climate, and see how we can use this to study, at least that's an idea, to study tipping points. So, I started from a picture which I showed last time as well, but I think I show every time because we show it every time. It's really relevant when we talk about climate. We have always to keep in mind that we have variability and non-trivial dynamics of a large range of scales in time and in space. And basically, each time we develop an approximate theory of atmospheric of ocean dynamics, what we do is we select a piece of these scales, and then we are left with describing what is coming in or going out from the other scales. So, and that is the basic problem of parameterizations. So this is, as we said, it's extremely hard to treat this problem. So I think it's a good effort to try to constrain and define global properties in a way that is somehow tries to take care of some of these interactions. So again, the climate dynamics is fueled by gradients of by energy flows and gradients of basically of heating rates across the domain. So that's very important. We have differential heating across the domain, and this comes from the fact that two elements that we have to keep always in mind, and that we will see today quite clearly now. So we have incoming radiation and of course outgoing radiation, and this radiation is absorbed and re-emitted in a very non-homogeneous way across the atmosphere and the surface and in the ocean. And the other element of differential heating is geography. That is, we have, if you want, the orbital parameters of the system. So we have, in fact, some areas of the planet which receive more radiation, and they have a surplus of radiation. If we look at the top of the atmosphere, we have regions who have a deficit. So if we are an alien spaceship and we measure the energy budget at the top of the atmosphere of our planet, and we don't know anything about our planet, we see there is a surplus. So incoming radiation is more than outgoing at the top of the atmosphere in the low latitudes. We have a deficit. There is a deficit of energy in the high latitudes. So you have to conjecture that there is a mechanism by which you have a transport of energy from the low to the high latitudes. And this is exactly what the geophysical fluids accomplish. And an element of last presentation that just to keep in mind the motivation of looking at the thermodynamics of climate and of the models that try to represent the climate is that, let's say, if we do an experiment where we force the climate for a finite time with, say, changing in the optical properties of the atmosphere or changes in the solar irradiance, and then we fix the parameters to a newly established value, we expect, in general, from any physical system, a behavior like this. So this is the radiative balance at the top of the atmosphere. Let's say we have a deviation from 0, where 0 is the steady state, and then we should have a relaxation effect. And so this is work done with Francesco Ragone, who is today in this room. And we have we have a transition between non-equilibrium steady state to another non-equilibrium steady state in the infinite future through a transient. And this is a pretty basic concept, but what we find is that the behavior of many models is more like this. So there are biases. So somehow there are biases in the initial state, steady state, where we should have on the average at zero balance, and it's not clear whether in the future climate the bias will be there or not. In fact, this is, I show you briefly. So this is the integration of an actual climate model, and also many of the very newest regeneration model have biases of this order of magnitude, which I think needs to be addressed. What one learns is that the main reason for these biases is an imperfect closure of the energy cycle and some errors in the treatment of dissipation and of the hydrological cycle. So we have that problems occurring at a smaller scale and processes related to instabilities of the system impact also the global energy budget if not treated properly. So now that's just to keep in mind that it's important to look at this sort of problems. Now if we look at, so this is a picture from colleague Axel Kleiden from Jena. I steal this picture very often, and this is a simple very actually correct and very precise representation, but quite clear of the non-equilibrium process in the Earth system. And the important thing is that we have gradients of temperature, of chemical potential, and we have fluxes, but these fluxes are not, unfortunately or fortunately, simple Onsager-like fluxes. We have nonlinear, very strongly nonlinear processes which basically live off equilibrium and coupling across these processes. So this is the very complex situation of non-equilibrium. We look at that the initial, of course, the driver of the equilibrium is the differential solar radiation. So somehow the point of what I think is that one way to try to at least give a description, a consistent description of the climate dynamics is to try to construct some thermodynamics out of it. So basically one can use some methods of classical, actually non-equilibrium thermodynamics to describe, to relate basically such gradients, the correlations between heating and temperature and the generation of kinetic energy in my system. And it's always important to keep in mind that if we look at, there is a very strong relationship between observing a non-equilibrium system, irreversibility, and the presence of an engine of some sort acting. So the basic characterization of thermodynamics of climate to me is actually that we have the climate is in a reversible system, generates entropy and produces kinetic energy from potential energy with a certain efficiency that we will define in a little bit, and we have keeps a steady state by balancing flows of mass, but that's not a big deal in this case, energy and entropy with the surrounding. The key element is that the organized fluid motion that I showed in the second or third slide that re-equilibrate the system from its radiative imbalance result exactly from the mechanical work due to this imbalance, and one can formalize this in a very clear way in the case of a quasi-geostrophic theory. So there is a closure problem here, which is why we cannot write a complete theory of this general circulation of the atmosphere without making assumptions, which in fact amount to putting part of the answer already in the question. So let's see how we can use some actually not so technical thermodynamic tools to construct, to study some of these properties and try to hint at ways to, as an example, understand mechanisms for climate transitions, and trying to construct new ways to characterize climate, which might be useful. Okay, so let's start. It's from the energy budget of the climate. So let's start really from a very basic thing. So the energy, omega, is the whole climate domain. So the total energy is given by the sum of the so-called moist static potential energy, which includes potential energy, internal energy, and energy related to latent to phase changes, and kinetic energy. So we break this integral, this is a very simple thing, into the sum of potential, and P is this moist static potential, but it is like our potential energy, and the kinetic energy. So this is nothing special. Now we want to write an energy budget, and since I am a physicist, I put a dot on the top of the letter, and I call it budget, because it's the derivative in time. So it is instructive, in fact, to start from compute, to look at this budget by looking at the budgets at the two pieces separately. So we start with the kinetic energy. So we have to ask ourselves who fits the kinetic energy, and who takes it away from the kinetic energy. So who takes away from the kinetic energy is actually dissipation. That is conceptually quite simple. And then there must be something else, someone giving, who gives energy to the bucket of the kinetic energy. So the only thing that can happen is a conversion mechanism between the potential and kinetic. Of course, we could have here some direct input of kinetic energy if there was a mechanical stir in the atmosphere. So if I conjecture the existence of a divinity that stirs my atmosphere, I would get input of kinetic energy. But as of now, I don't have evidence of such a divinity. So I remove it. So one can prove that this conversion is actually a work in the thermodynamic sense, and is related to the pressure, to work done by pressure gradients. Okay. Now, if I look at the budget of this potential energy, of course there must be minus this quantity, this conversion, and the rest, in fact, is heating. So the heating, that's how the sun, and not only the sun, all the rest, but let's say in first place the sun impacts my energy budget is in this way. And we see it here. So here I have a convergence of fluxes, of radiative fluxes, latent and sensible heat fluxes. And the other part, which actually was related to the slide I showed before, negligible in the global sense, role is played by dissipation of kinetic energy that has to become at a certain point at the bottom of the turbulent cascade some heating. Now, if I sum these two, I get a nice. Yes, the battery. Yes. Oh, it's there. Okay. So basically, if we sum the two, we get that the total energy is impacted. Yes. Only by fluxes and orders, as we. Okay. Now, let's see how we can use these properties. So Johnson proposed in 2000, in a very interesting paper, this construction. At each instant, we break our domain into pieces, where I have heating and where I have cooling. This is a very simple thing. I can always do this operation. Of course, the border will be, the boundary between these two regions will be very complex, but we are not interested now in the geometry, just in the fact that we can do this. Now, so that's, so just let's keep in mind that the plus refers to heating and minus to cooling regions, okay? Now, let's take long-term averages from before and assume steady state. So, of course, stationarity imposes this condition on the average derivative of energy in all its forms. So, from immediately, while looking at at this part, and imposing this, that the average of the derivative of the kinetic energy is 0, we get that the work in the average is equal to the dissipation, and by the second law of thermodynamics, this is positive. Okay? So on the average, we have conversion of potential into kinetic energy, and also that this work is equal to, guess what? The differential heating. So the difference between the heating in the warm and the heating in the cold, okay, parts. So this is actually a very simple way to look at the so-called Lorentz energy cycle, which says that the circulation is powered by differential heating through a conversion from potential to kinetic energy, and then we have dissipation. This is actually a pretty simple energy balance. So that's an energy balance where I'm starting, though, to separate the different forms of energy. And I have introduced temperatures. So I am going towards some entropy, basically, which comes now. So I don't want to go. Let's say if I assume local thermodynamic equilibrium and I neglect mixing, which in this case is not so relevant, I have that in order to construct the budget of entropy, I just have to put T, a denominator, where everywhere I have heating. And note that this term are positive. I call this S dot plus and minus, are positive and negative exactly where Q dot plus and minus are positive and negative, because T is positive. Okay? So everywhere I'm heating, I am getting a positive S dot. That's the first element. Now I integrate over these domains and I construct the sigma dot plus and sigma dot minus. So these are extensive quantities, these are intensive quantities. Okay? So at each instant I will get these values, and they at each instant will refer to different volumes, regions, depending where I have heating and cooling. So that's what it means. Now, if I take the long-term average of this S dot, it has to be 0, just like kinetic energy. So this means that the average of this sigma dot plus and minus is equal and opposite. Okay? Keep in mind, the average of phi dot plus and minus was not equal and opposite, because phi dot plus was larger in absolute value than phi dot minus, because the algebraic sum gives me the work which is positive. Okay? Okay, now let's do a little step, and I can construct, there is, since at each instant this sigma dot and this phi dot are defined in the same domain, well, I just take it's not even a mean value theorem. If I take the ratio between phi dot plus average and sigma dot plus average, I get a temperature. And for the properties I told you before, so this is positive, 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 negative, negative, positive, we get that theta plus is larger than theta minus. So this corresponds to an average, in some sense, hot and cold reservoir. And what you obtain, this is quite nice, that the work is equal to, guess what? Theta plus minus theta minus over theta plus times phi dot plus. So I can introduce an efficiency. So this is a Carnot efficiency in the sense that I have a relationship between heat sources and sinks and temperatures. Nobody says that the climate is a Carnot engine, because it is as irreversible as it can be, but this is the engine which has the same efficiency when I consider these inputs of and outputs of energy, and such that I have the right value for the work. Okay, so I immediately have a new climate observables, the efficiency, which is a good characterization of how much, if you want, larger temperature gradients measured in terms of the heating, the corresponding heating rates. So if I have a system where heating and cooling occurs, like in a white noise, this will be 0. So it gives me a measure of how organized is the system somehow. Okay, now I can. So this is the step. Now, if I, if you're a physicist and you don't know how to proceed, usually you open a book of Landau and you try to find something, and it is useful. I was also you find a lot of useful ideas, of course, always. And so, as an example, you find there is in one small alpha page, there is a small comment on the minimum amount of entropy production a system which has a certain heating and a certain temperature must have. So if you use this and do some modest, let's say, simplification, you get that this minimum entropy production is related. First, is given by this efficiency times, which is a small number, these entropy fluctuations that you get due to heating or cooling. That's the first step. Now, if you look at what is the minimum entropy production, well, the minimum entropy production you can have in a system compatible with the existence of an average dissipation rate epsilon squared is just this. Because if you have dissipation of kinetic energy, there is no way you're not going to have this entropy production. And then there is the rest. So this is the minimum. So if you give me a system, I know there is all this dissipation of kinetic energy, and you don't tell me anything else, there's going to be at least this entropy produced inside. The rest is, of course, the contribution of fluxes inside the system. So fluxes down temperature gradient. So at the end of the day, what are the two basic? There are three basic mechanisms to produce entropy: dissipation of kinetic energy and fluxes across temperature gradient, or if you want, fluxes of matter across gradients of chemical potential. But here we are not in the last part is not relevant. So we see that this part is the S min, this is the rest. So we can construct, we can quantify the excess of entropy production with an index, which we can call index of irreversibility, that tells you what is the excess of entropy production related to the minimum you could have. And there is an index in the literature, in the engineering literature mostly, by Bejan, Adrien Bejan, who used this to study convection problems, basically. Okay. So let's keep in mind, if I have strong transport across temperature gradient, I have a lot, alpha is big. Okay? But if I have a lot of transport across temperature gradients, I kill temperature gradients. So this reduces my my ability to create mechanical energy, to transform. So what we get is that if you write the entropy production, it gets a form like this, where I have a product of eta n1 plus alpha. So in other terms, one can say that I have a lot of entropy production if I have a joint optimization of heat transport, which has to do with this alpha, and the production of mechanical work, which has to do with this eta. So if I have a system that immediately thermalizes, I have zero entropy production if the system is extremely fast in killing temperature gradients. If my system basically does not kill temperature gradients, the transport will be very small. So that's just a qualitative statement. Now, if we go now into the climate system and we want to compute entropy production, we discover that there are two independent ways to start to compute it. This was introduced by Good in 2000. At least that's the best reference I can think of. So if you write that the balance, entropy balance of the Earth, you have a part which is related to material processes, and one part which is exactly what I showed you before, and the part which is related to convergence of heat of radiation fluxes. So these are called the direct formula, which is the one I showed you before, and this is called the indirect. Note that there is a sign minus in between. So we can compute, in fact, this is a very nice thing, entropy production in our planet either by looking at the fluid properties or by looking at the optics. So the optics tells us everything about the entropy production through this relation, which I find it quite interesting. So you can use this and compute entropy production, and the number you get is of the order of, this is a number to remember, 50 milliwatts per square meter per Kelvin as average rate of entropy production of our planet. This is the kind of number we get. Okay, now you can start from this formula, and this formula, remember, I have only radiation here. So if I do some approximation, I can treat the problem, and I know that most of the shortwave radiation is absorbed at surface, so that atmosphere is, to a very fast approximation, transparent. I can construct an approximate formula of entropy production based only at radiation budgets at surface and at the top of the atmosphere. And what I can see is that, so this is only from 2D averaged radiative fields. So we go from a 4-dimensional need of 4-dimensional data, 3D plus time, to a 2D time independent. There are approximations, but one nice thing we get is that you can separate the effects of vertical processes. You see here the difference between the emission temperature of the planet and the surface temperature. So at each location, we are looking at the vertical fluxes and how this impact entropy production. And there is another part that one can prove is related to large-scale horizontal flows. So this is related to north-south gradients, and this is related to surface upper atmosphere gradients. Okay. Okay. Let's. You can basically characterize the thing, the entropics of the climate system as something like this: exchanges between surface and upper atmosphere in the low and high latitudes, and the transport between north and south, between, of course, the atmospheres. So that's a simple model. Okay. Okay, this is, you can use this to study full GCMs, because it's really easy computationally. And what we get is that the question is, what matters most? Does it matter more the vertical processes? Do matter more the vertical processes or the horizontal processes? So in other terms, in terms of irreversibility, is the vertical mixing more important or the north-south transport? And the answer is that the vertical mixing dominates by a factor 10 to 1. So to a first approximation, which is not bad, in terms of irreversibility, the climate is a collection of vertical columns of air that mix, and which are weakly coupled among them. So that's, I think, a nice information we get on this. So we learn something on how to construct simple model of climate. And the most of entropy production takes place, guess what, in the tropical regions. And we can see, look, these are rates of entropy production. We see all the features that we usually associate. There is the warm pool here. We have the lack of hot water in this part of the Pacific, and that's what El Nino is about, and so on. So we get a really nice characterization of climate using these observable. Okay, please.
You have not discussed how it depends on space, right? You just
no. This is a density of entropy production.
So basically, you say that it is more important in the vertical than in the horizontal.
Yes.
Here we also see that it is much more important in the tropics than in the. Is it true?
No, yes, okay. So basically, this is, okay, when you look at the horizontal, what you get is basically an entropy flux that closely cancels out. So if you look at so the vertical part is well defined because you have the mixing. So the first information is that, guess what? The entropy production in the vertical is positive everywhere at each point of surface because you are really mixing vertically. So it must be positive. And geographically, it is dominant effect in the tropics, because where you have deep convection, mixing, and very powerful processes. This has been, here we are not looking at the nice thing, this has been computed only using radiation. So forgetting about dynamics, and still you get the signature, basically.
Can you discuss the spatial structure for the second part?
The second part is actually much less interesting. The second part, you have negative contributions where you have entropy fluxes. So this map, just to tell you that if you look at the numbers, here you have large fluxes, but they cancel out almost exactly because the temperature gradients north-south in the emission level are not that big. So it's a small effect. So this is somehow, if you look at numbers, this seems larger than this actually almost everywhere, but once you integrate, this means nothing. This is very small. It's 1/10 of this. Now, again, but if we want to use these properties for climate models, we need to be able to use flexible climate models. And one model we have been using is the model that has been developed in the theoretical meteorology group in Hamburg. Well, before I came, it's called the PLASIM, and it's a model. It's basically a climate model with many features, but which is like with a simplified description of some processes. So we get a very good feeling of global climate dynamics and response without retaining all the details. But if we want to look at large-scale properties, might be not necessarily we need all the details to study them. And also, there are a lot of, this model is flexible, so we can study a vast range of climates. And yeah, this model actually, for those of you who are interested, has even a graphical user interface. One can play as an example by killing some spectral modes and so on. One can change the orography, can change the properties, the orbital parameters of the system and the CO2 concentration. So it's a very good model to do what, to study a vast range of climates, and now we are using it also to implement the dynamics of Mars and other planets, because it's actually a flexible model. So what we have used, we have first used this model to study a classical problem of dynamical paleoclimatology, which is the problem of the transition between snowball and snow-free. So this is the prototypical problem of tipping point in climate science. So we have also paleoclimatic evidences, and we have a long list of models from very simple to very complex, which give you, as always, this behavior. So for the present climate conditions, in terms of CO2 and so optical properties of the atmosphere and solar radiation, we are in a relatively warm state, but everything is compatible with the existence of a very cold state, where we could well be, which is a state where the average temperature of the planet would be about 50-60 degrees lower than now. And it seems that 700 million years ago we were something like here. And actually it's not clear how we jumped here. So you understand that the climate is in fact multi-stable on a vast range of parameters, which is, I think, extremely fascinating. And this is related to the so-called ice albedo feedback. So look, this is the solar irradiance, and this range of bistability is order of 10-15%. So it's a very big range. So somehow, what does it mean? That if I decrease the solar irradiance beyond this point, I will jump to this cold state. If I raise it again, I will jump to the warm state only when I have done a big overshooting. Okay? So that's the basic property. And the classical way of showing this is plotting against temperature. So this would be, here I have a very strong bifurcation. Here the planet is entirely ice covered. Yes?
What is the resolution of the model?
This is a T21 model. So it's a resolution of order of 5 degrees. And you get, but this feature is very robust. You can get it with the energy balance model, Budico, Sellers, Gill, 60s and 70s, and any model will give you, so this is a very robust feature, and we also get it. You can get this feature also with more complex models. So this is, let's say, a property of our climate. Okay, of course, as an example, we start to look that temperature grows with the solar irradiance in both cases, which seems trivial. Okay, but let's keep this in mind. Now, let's plot the efficiency. So up to now, we have characterized these two climates as being one cold and one warm. So it's just a matter of average temperature. Let's see their dynamics. So let's take a quantity that describes the relationship between temperature fluctuations and heating rates. So the efficiency I introduced before. So blue is cold and red is warm. So in the warm state where we are, if I increase the solar constant, so if I increase temperature, the efficiency goes down. In the cold climate, if I increase the solar constant, so if I increase the temperature, the efficiency goes up. So in this world, in our world, warmer temperatures are associated to smaller efficiency. So the system becomes thermally more homogeneous if it gets warmer. In this other world, if the system gets warmer, temperature becomes more different across. So this is totally different properties. So these two systems are not just warm and cold. They are totally different worlds. So that's, I think, it's a good image. So what is the reason? The physical reason is that in a warm climate, if I warm up the climate, I have more water in the atmosphere. The water is a fantastic, provides a perfect tool to mix, to kill temperature differences, so that this becomes an hydrological cycle-dominated world. This is a totally dry planet. There is basically no water in the atmosphere. It's all stored as ice. And if I increase the radiation, you get changes in the albedo. Sometimes you get something melting, and more importantly, you get changes in the vertical stratification. In other terms, the constant n squared you have in the quasi-geostrophic theory decreases. Okay? So you have a more energetic circulation. So that's what you get here. Now, interestingly, look at what happens in the transition. So I am cold, I'm warming up, this grows and then jumps to a much lower state. Same here. I'm warm, I decrease my temperature, and then I jump, and it decreases. Jumps to a lower value. So my interpretation is that, okay, this eta gives me a measure of temperature difference, gives me a measure of how good my engine is. Each time I lose stability, my system becomes a worse engine with smaller temperature gradients. Actually, it's okay, because what does it mean that the temperature differences become large? This means that the negative feedbacks that try to keep my system under control become weaker and weaker until at a certain point, boom, the system explodes. Okay? So that's, I think, the link, a good link you find between dynamics and thermodynamics. Okay, now, if I look at entropy production, it looks like a temperature. That's a very important thing. This graph looks like the graph of temperature. So this is, in some sense, the real temperature of my system. The average temperature does not make much of a sense in an equilibrium system. This is a better indicator for me to characterize the system, and also the difference between corresponding state of entropy production is, instead of being 20%, so 50 degrees, in temperature is a factor of 4 or 5. What gives all this huge difference is that in the cold state there is no hydrological cycle, as I said. So most of the entropy production is due to mixing, to the phase transition in the hydrological cycle. So who has the lion's share of irreversibility in our climate is the hydrological cycle. In other terms, if I want to describe climate without the hydrological cycle, I am losing all the interest, I mean not all, but a lot of the interesting ingredients. Okay? And if we use this index of irreversibility, we find that this system has alpha close to 1, and this system has alpha close to 5 to 10. So here the dissipation of kinetic energy contributes about as much as fluxes here, because it's only negligible. Negligible, it's smaller. Now let's keep this. And just saying that we can repeat the same experiment. Instead of changing solar irradiance, we can do a more classical, let's go 1 second, climate change experiment and change CO2. So we change CO2. By changing CO2, we stay in the warm, we never fall into the cold regime, and we can construct sensitivities of thermodynamic quantities like efficiency, intensity of the energy cycle, entropy production, irreversibility, with respect to CO2. And we see that higher concentration of CO2, so higher temperatures, increase irreversibility, increase entropy production, decrease efficiency, and decrease the intensity of the energy cycle in actually pretty linear way, as we hoped for. If we can now bring these things together. So we can, instead of, before we have spanned this direction, so along solar constant, then we have spanned this direction along CO2. Now we can, boom, do more simulations where we change CO2 and solar constant and try to construct a manifold of the properties of the system. So what you find on the left is the cold, on the right is the warm state, and the purple line indicates the tipping points, in fact. So the rule is that if I am in the cold and I change quasi-adiabatically my parameters and stay always here, I will stay cold. If I cross this purple line, I will jump to warm and I will end up here, and so on. So this is the characterization of efficiency. So we discover that in fact the properties that efficiency increases at the transition is not an artifact of just changing the solar constant. This is a very general property, I find. Whichever is the direction over which I approach this line, efficiency grows and goes to a lower value. And same here. This is the temperature, which is not so interesting. Entropy production behaves less central. So this is the kind of 3D picture you get that extends the other picture I showed before. Here is the solar constant, here is CO2, and these are the manifold of the two coexisting climates. So this is somehow a planetary exploration. Now, the question is, if I can add other parameters, I can add, many other parameters I can change, but of course if more parameters say, look, I gain in completeness, but I lose focus, so what am I studying? So can we try to relate, to find a consistency between these changes? So can we construct some parameterization that gives us some sort, of course, of approximate universality in our behavior? So as an example, let's plot emission temperature, so which is what someone would observe with the telescope, to the entropy production. So these are, look that this is a good approximation, a 1D graph, but this comes from a 2D parameter exploration. So we have that things project. So TE is a good predictor of S math. So if I observe this, I know S math, even which can be realized by different combinations of CO2 and solar irradiance. So this is the emission temperature. So again, this is a quantity that describes the equilibrium properties of my system against the dissipation. So looking at some equilibrium property, I learned something about non-equilibrium properties. S math, this is the dissipation, and this is the efficiency, where this indicates the tipping point. So somehow I am able, using the thermodynamics, I try to find some universal property. So if you tell me that the planet has this emission temperature, 260, I can predict its efficiency. These quantities are in principle totally unrelated. Okay, and this corresponds to a many different kind of combinations that give me the same emission temperature. So there is a nonlinear relation that is not trivial at all. And that's also quite interesting. If you give me the emission temperature, I can give you the meridional heat transport. So I can relate a property of the mean to a property of the variability, which again is not constrained by the equations in any sense. Okay. Now, what happens if I change? One can say, okay, but here you have changed only the radiative properties, basically. What happens if you change, say, the length of the day or the length of the year? So you change the dynamics, and the dynamics would change a lot if you change the rotation property of the planet. Well, this is, as an example, the same graph as before is the purple, and the black is the relationship you find by halving the length of the day. So it's a planet which rotates much faster, and its dynamics will be different. We will have different cycles, different tropical circulation, but still this relationship is extremely strong. And so seems to have some properties seems to be quite relevant. If you look at the efficiency, you can see again the black spots and the purple circles, they fit very well. So this seems to be something quite general. The heat transport also has same properties, and so there seems to be consistency in our ability to relate these two. Why? I have no idea. But not no idea. But of course, I don't have an answer. But so this seems promising from my point of view. Now we can play another little game, and we can decide. Let's change the length of the year. So let's move the planet, if you want, from being far from the parent star to closer and closer. Note that the exoplanets that people have been finding in the last years have usually a length of the day and have a length of the year comparable to our length of day, and they are also phase locked. So they always face the star with the same side of the planet. So here it's the same, it's our Earth, by just reducing the length of the year, and of course keeping the irradiance constant, otherwise everything changes. And this is the same graph I showed you before for temperature. So let's see what happens by changing the length of the year from, this is about, in fact this is already 30 days, few days, 2 days, and 1 day, phase locked. We see that the bistability is lost. So if the length of the year is small, the system loses its snowball, snow-free duality. And you can construct something like this. So this is the width of the bistability, and it has this nice property. So this is 2 days. So length 1 year equal 2 days. I have no bistability, and then suddenly, boom, it jumps like this. So it seems that somehow you are able to capture some transitions in the properties of the system. These transitions are relevant because when you're trying to explore planets, you want to determine the necessary condition for the existence of water in the liquid form as potentially necessary condition for life. But if my planet can be in 2 states given the same orbital parameters, so if it can be snowball or snow-free, I need another characterization, which is 0 or 1, snowball or snow-free, because if it's a snowball, there is no life, or very, 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 very hard to find. So here we have a relationship between the dynamics and the possibility of being in one of the 2 states. Okay, so coming to the conclusion, I think that using some tools of thermodynamics, we can learn a lot about climate, and we can study properties like the tipping points, as an example, and we can characterize climate change in a consistent way. We have, of course, that's I think quite important. We can learn how to characterize, give scalar quantities describing climate, which put together dynamics and thermodynamics. This can be very good for classifying the performance of climate models. So that's one of the possible tasks. Another task is to study consistently the thermodynamics of celestial bodies, and it is something which we are working on. And something that I will talk about during the rest of the program is instead of going to the macro, going to the small scale. So studying how entropy production changes when I perform a coarse graining in the physical space and in time on my field. So this will try to ascertain the role of different processes at different scales in the reversibility. And instead looking at other side on tipping points using a mathematical approach of EVT. This is work done with Salvatore Pascale, who is also working on this. This is work done with Paul Manville and Davide Faranda and Jeroen Bauer. Okay, thank you very much.
What kind of tipping point did you get?
In where? In this?
Yeah. No. Your model.
Yes,
Yeah.
this is this tipping point. So,
what kind of?
yeah, it's the snowball.
RB and RB. What kind of tipping point?
It's not tipping points in general. We have studied this transition. It's a transition between snowball and snow-free. So it's a very specific.
Yeah, it's tipping point, but bifurcation. Yeah.
Yes.
What kind of bifurcation?
I don't know if you can. I mean, it's it's. I think it's a sudden bifurcation, but I'm not sure. But this is not my scope here. I'm not. I mean, anyway, this is a bifurcation in a very highly dimensional space. It's not a fixed point. So, and my goal here is not to look at the dynamic. That's exactly the point. I am not. I don't want to know. I cannot compute that bifurcations on this system. Okay, I can do it in a simple system, and there is very good work to do this. But this is here I have a transition between two turbulent states. Okay, so it's not. I don't think it's not so interesting to study this bifurcation as a mathematical transition of the system. The point is the details of it. The question is, can I find a quantity, a global quantity that tells me something about this bifurcation? Okay, that is to me, that is the rationale behind this. So can I construct a thermodynamic indicator that gives me interesting result on a mathematical object that it's impossible to study? Of course, if we go to one-dimensional Earth balance model, or even to a zero-dimensional model, you can study this bifurcation. I mean, that's the work of, I mean, actually partly stochastic resonance come from this kind of analysis. But anyway, there is a lot of work you can do there. But this is exactly what I don't want to do. So what I want to do is to look at macro properties. So, but one, I think you can use an idea like this to study other systems, because this is, as you see, this is just an excuse, and I have chosen a very strong, powerful, the biggest tipping point you can think of, basically. But if you take a system and you construct a function that tells you its efficiency, I bet that you can use it to very efficiently to study transition between different regimes, because these different non-equilibrium regimes will be defined in the first place by a quantity like efficiency, because that's the essence of the non-equilibrium. That's my general guess. Observation is that here it seems to work, but it's not general. I mean, I would not claim that. Just my personal idea.
Okay, otherwise, you did study the phase transition, and you did get a critical point for the phase transition. What it means physically?
Where? Here? Here? Yeah, this here. That's where
you identified critical point for the phase transition.
Yes.
It means physical.
Yeah, it's the ice albedo. There is a mechanism which is ice albedo feedback, which is basically what happens is that you reach a critical latitude of sea ice extent, beyond which, if you freeze a square centimeter of ice, you will basically freeze the whole ocean. That is the effect. That's when this feedback becomes positive. So this is a very powerful mechanism. In fact, you find it's very interesting. You find almost if you put a model with the solar constant and blah blah blah, and both very complex model, intermediate complexity model, energy balance model, you get this value here, if you want, almost to the same result, because it's related only this 1200, 10% below now. It's related to the simple radiative, the optical properties of ice. So if you give me another ice, it will change. But being ice white with that property, it's a very universal property.
So these tipping points are probably not relevant for the current climate change debate.
No.
Is there anything you could say about sort of smaller, maybe more localized?
No, yeah, you're right. I mean, this is, so the exercise here was also stimulated by conversation with colleagues in astrophysics, because to study planetary atmospheres. But I'm not sure, the question is, each time if you go through a tipping point, I mean, as an example, say, collapse of thermal circulation, okay? So you can diagnose it in many ways. Of course, you can construct, I'm not sure whether you will be able to see something like that in a global climate indicators like this, but somehow I believe this can be a method that can help you in principle to characterize tipping points with a global effect, because here we are integrating over the globe, because that's what we need to do the energetics with. So, of course, it's not a tool to study any tipping points, but let's say, I think if you want to, somehow, if when you study the instability that leads to an hurricane, kind of work of Kerry Emanuel, I mean, probably you can use exactly the same. It is somehow it's a tipping point for that system. If you can close the energy, so if you can put a virtual wall and close the energy budget, then you can repeat this, and you will. I mean, if you have a transition between two non-equilibrium systems, you will see a signature of this sort. Then I don't know if this indicator is the right one, but I think you can construct an indicator with this spirit to do it. So it can be a primary productivity, if it's a biosphere, something like that, usage of flux of matter. I think you can do something like that. But I don't know how to do it.
I have one question more.
Yes.
We discussed already about different kinds of tipping points, bifurcation in these tipping points, and so on. What kind of tipping point did you get in this classification?
This is
DRM, noise, rapid.
Yeah, I don't like the acronyms. I refuse to learn the acronyms. So, but it's this is a parametrically. It's you get. I mean, of course, you can jump from one state to the other in many ways. In this case, we have just done a parametric modulation. So there is no time in this. Okay, it's just a quasi static modulation of a parameter. Of course, if you move, I mean, I can tell you that if you move, change the solar constant with a finite rate, you will jump before, of course, because you will as soon as you get a positive fluctuation of sea ice extent, the system will plunge into the cold state, and you will never get it out. In fact, one of the questions is, if we were, as it seems definitely that we were, here, okay, how did we jump here? And it's not trivial. So, of course, it can be volcanoes, can be gigantic Mars-like planet hitting us. So just warming the planet, because these things are in any more or less virtual energy landscape you can think in between, incredibly different. So this is very extreme case. So as these quantity measures, if you want.
Okay, any more questions? So let's thank Valerio again and then have a lunch.